Welcome to another mathology video, a very special mathology video. Special how? We'll see. Today I'll talk about the parity of permutations, a very important concept within mathematics. Non-mathematicians don't know much about it, but it's really, it's really the yin and yang of mathematics. It's incredibly important. For example, for figuring out what's possible and not possible with these permutation puzzles, but also for figuring out a determinant. So most of you, many of you will have seen determinant in linear algebra. The explicit formula for the determinant involves permutations and the parity of permutations. And of course, the determinant itself is taking a square array of numbers and distilling all the entries in this array into one number. And that one number, although there's a lot of loss of information, of course, that one number can tell you all kinds of amazing things about different important objects associated with the square array, for example, linear transformations or systems of equations or sets of vectors. But we'll get to all this. So to start with, what's a permutation and what's its parity? Okay, so here we've got tiles, 1 to 8, could be more, could be less, in their starting positions. Tile 1 is in position 1, tile 2 is in position 2. I've connected the starting position with the tile with an arrow. That arrow will follow the tile around all the way throughout, okay? Now we're going to permute things, shuffle things up. That's a permutation, and its parity is odd. Okay, that's another one, that's another one. They're all odd permutations. There should be an even one somewhere here. Even permutation, great. So it's either odd or even parity, okay? Odd or even permutation. Okay, now why is this, for example, odd? Well, because it's got 17 inversions, and 17 is an odd number. Now, of course, immediately I have to tell you what an inversion is. That's very easy. So you just look at pairs of tiles. If they're in order, in ascending order, then no inversion, otherwise inversion. So 7 and 5, that's an inversion because the 7 is greater than the 5. 5 and 8, not an inversion, 5 smaller than 8. 8 and 3, that's an inversion. 5 and 3, that's an inversion. 8 and 1, that's an inversion. 8 and 2 is inversion. 2 and 6, not inversion. You get the picture, okay? So you look at all possible pairs of tiles at the bottom, and some are inversions, some are not. Just count them up. 17 in this case, and 17 is an odd number. So the parity of our permutation is odd. Okay, now we're mathologer people, so we want to see this as visual as possible. And actually, you can see those inversions at a glance in this permutation diagram. They correspond to these crossings here. And let's just count the crossings. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 inversions correspond to these crossings. And why should a cross like this correspond to an inversion? Easy, right? Because the initial positions here, they're in ascending order. So for example, 1 and 4, right? So 1 and 4, ascending order. But at the bottom, 4 and 1 are switched, right? So inversion. And then of course, because the arrows are pointing this way, the arrows have to cross. Okay. And then if they're in ascending order at the bottom, then the arrows won't cross. All right. Now, reset. This is actually, doesn't look like it, but that's actually an permutation. This is called the identity permutation, the do-nothing permutation. Mathematicians love this sort of stuff. And of course, there's no crossings here, so there's 0 inversions. And so 0 is even, so the identity permutation has parity, even permutation. Okay. There's other special permutation swaps. If you just have two tiles swapped like this, that's a swap. Or like that, that's a swap. Actually, it turns out that swaps are always odd. Let's have a look. So that one is, for example, is odd. That one's odd. Okay, so I mean, just kind of looking at the symmetry of something like this, it's probably pretty easy to figure out why they're odd, right? But we also get to a more detailed view later on. Okay, now there's something else I have to tell you about swaps. If you have a random permutation and now you take two of the tiles and swap them, the permutation changes. And actually it changes in such a way that the parity always flips. Have a look at this. So we're doing a random swap, parity is flipped. Okay, swap, parity is flipped. Swap, parity is flipped. Not clear why this is happening. Not clear at all. Will all become clear later on. Just remember it for the moment. Okay, so things to remember. You know what a permutation is. You know what inversions are. You know what parity is. And you know how to figure it out just by kind of looking at the diagram, for example. Okay, and then the other thing that's really, really important, is probably the most important thing to remember so far, is that when you do a swap after a permutation, the parity flips. Okay. One more thing I have to tell you about permutations and swaps. It's like this. If you start out with a random permutation, you can take this back to the identity permutation by just doing a couple of swaps. Why? Well, how? Well, 1 is currently not in the right place, so we could just kind of take the 5 and the 1 and swap those two guys. Then 2 is in the right place, we don't have to worry about it. Then we can take another swap that swaps the 8 and the 3, and that takes the 3 in the right place, and keep on going like this. And let me show you how this works. So there, 1 in good place, 2, 3, 4, 5, 6, all in place, just by doing a couple of swaps. Okay, so now, of course there's, we can do this again, just for this one maybe again, okay. That's one scheme, but here's another scheme of putting those two guys back in order. So there. And in fact, I could just kind of start out kind of going blindly and not get anywhere with getting back to the identity and get maybe like a 1 million missteps, and then by chance get back to the identity. So lots and lots of different ways to get back from this permutation here to the identity. Very different ways, but there's one thing that all of them in common, and that is this. If the parity of our permutation is odd, then it will take an odd number of steps. Right? So you'll absolutely not be able to get back to the identity with, say, 4 steps or 4 swaps. Okay, so why is that the case? And let's just check it quickly. So for this one here, for example, let's just count, right? 1, 2, 3, 4, 5 swaps, okay? And with that scheme here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 swaps. Both on odd numbers, okay? And pretty easy to see, why should this be the case? Well, we're starting out here with an odd permutation, okay? And we're aiming for identity, so that's an even permutation. So we're going odd. Every swap we flip, right? Parity. Odd, even, odd, even, odd, even, odd, even, odd, even. And so to get from odd to even will take an odd number of swaps, and to get from an even number, from an even parity permutation to another even parity permutation will also take an even number of steps. So that's really important. Okay, so 2 things to keep in mind. So just etch it into your memory. The first one is a swap flips parity, and the second one is it will always take an even number of swaps to sort out an even permutation and an odd number of swaps to sort out an odd permutation. Cool. Now, just want to mention this. So we have a random permutation here. We do random swap that flips the parity. That's just a special case of something much more general. So instead of having a random permutation followed by a swap, we can actually have 2 random permutation in sequence like this and combine them. Okay, so what actually gets permuted and how? Well, let's just animate it. Start out with the tile in their original positions, then the first permutation permutes them, shuffles them around, and then wherever they are, you start out and apply the second permutation, and that's the result of putting both permutations together. And kind of just as a permutation diagram, it looks like this. You can put the crosses in, can count them, and in this case we're going to have 19 crosses. And if you had counted the first one, it would have been 14 and 13 crosses. And 14 and 13 and 19, well, I don't know what they have to do with each other, I don't know. Here's another scenario, 10, 22 and 20. There doesn't seem to be a real pattern there, but there is a pattern here in the parities. We just have a look. Even, even, even. Even, 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 even. Come on, give me something else. Odd, even, odd. Even, even, even. Odd, even, odd. Ah, even, odd, odd. And actually, you probably guessed it already. So these things add like numbers. So even number plus odd numbers, odd number, even parity, odd parity, odd parity. Even plus odd is odd. Odd plus even is odd. Odd plus even is odd. Even plus odd is odd. Come on, give me another one. Give me another one. Go, go. Even plus odd is odd. I want one even plus even is even. There we go. Okay. So anyways, this always works. It's not clear why that's the case to start with. And kind of when you think back to what I said about second permutations being a swap and therefore this being odd, well, then it kind of fits in with what I said before, that things flip, right? Because if you say even plus odd, that's odd, or odd plus odd, that's even. So things always flip when you add an odd to it. Okay, so pretty good. So now we're actually in a pretty good position to actually apply all this stuff. And first I'm going to apply it to something very famous, the 15 puzzle. Okay, so you've all played with this sort of thing. These days, the way we play with the 15 puzzle is we've got a box, 4 times 4. We've got tiles numbered from 1 to 15 in order in the box, okay? And now we shuffle it up by taking a tile adjacent to the empty square and just kind of push it in. Push it in, 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 push it in. And kind of keep on going like this until we're kind of back with the empty square in the lower right corner. Okay, now if you have a look here, it says 12 steps. Well, it was 12 times pushing, that's clear. But then it also says inversions and parity even. So we're somehow talking about permutations here. But what's being permuted here? So for example, if I'm here, right? I mean, the tiles are sort of not in the same place. The empty tile is somewhere else. So this is still supposed to be, you know, inversions here somewhere. Well, what's really happening actually is that we've got one more tile here, and this is a ghost tile. So we actually interpret this empty square as a ghost tile 16, and then kind of pushing it into the empty square corresponds to just a swap of two tiles. Isn't that neat? So that really fits in nicely with what we've been talking about so far. So we're permuting things. We're permuting 16 tiles by swaps. Okay, so let's just do this. So we're starting out like this. Okay, we're starting out like this. And now we're going for shuffling up. Okay, so shuffling up. So as we shuffle up, the empty squares kind of travels around here. Kind of speed it up a bit. Okay. And then the 16 is back in the lower right corner. And now what it says up here is we're dealing with an even permutation. Okay, so now it's clear what it means. Okay, and well, let's just do it again. So just shuffle it up again. So random number of steps and also random walk in here. And the parity is even again. Okay, round trip again. Okay, very nice, even again. And just in case you're wondering, is this a coincidence? No, it's not a coincidence. When we do this shuffling like this, 16 starting here and ending here, we're always going to have an even permutation. Okay. And actually, I can prove this to you fairly quickly now, based on what I told you before about swaps and swaps flipping parity. It goes like this. So what you do is you highlight a checkerboard here, and then let's just see what happens to the 16 as it kind of moves around as we shuffle things, right? So slow motion on, round trip. So at the moment, 16 is green. Now it's red, green, red, green, red, green, red, and so on. Okay. So then what happens throughout here is it's always green, red, green, red, green, red, green, red, and then green again. So what that means, since things alternate green, red, you've got the same number of greens as reds in here, and that means that the number of steps is always 2 times the number of green or 2 times the number of red. It's an even number, okay? So we're taking an even number of steps always to get from here back to here. And of course, every step corresponds to a swap. We're starting with the identity, okay? So we're starting with the identity, which is even. And we're taking an even number of swaps. And what I said before is that we then automatically end up with an even permutation. How neat is that? Okay, so what we've just proved, assuming that this whole flip business works, is using parity of permutation, that in the 15 puzzle, using legal moves, you can only ever produce even permutations. So what that means, for example, is that if I just top out the box, all the tiles, and put them back in randomly, there might also be odd permutations coming out, and that odd permutation can then not be solved, kind of just shuffling tiles around as it's allowed. Pretty good, right? In fact, it turns out, and it's easy to see, there's an equal number always, doesn't matter how many tiles you have, there's an equal number of odd and even permutations. Easy to see. So say all the odd permutations are here, all the even permutations are here. Take a swap, one swap, and apply to all those even permutations, then all the even permutations will turn into all the odd permutations. And if you take the odd permutation and apply the swap to this one, it will turn into an even permutation. So they have to be the same, right? So the same number of even and odd permutations. So then in the case of this 15 puzzle, when you kind of toss it out, you have a 50-50 chance of ending up with an even permutation. And actually that's a fairly easy puzzle. So it's actually very easy to figure out that all even permutations can be solved. And so you've got a 50-50 chance of actually being able to solve this puzzle here, which is nice. Okay, so how are we going so far? Pretty nice, pretty understandable. Hopefully I didn't lose you anywhere. Now, I should probably say something about this app that I'm using here. So this app that I'm using here, I built this myself. And what I want you to do at the end of this video is just go to the description and click on the link there, which will take you to a page that has this app. It's actually a JavaScript app. So, if you feel like doing so, if you're like really keen on trying something deep with this, you can just download the code and you can actually extend it. You can put other features in, other permutation puzzles that will work with this. So there's all kinds of other features that you can explore to start with. So for example, I've also have this puzzle in here, so you can do all of these sorts of things. You can checkerboard it, you can do round trip, all of these things. You can go maybe to that single view again and play with 16 tiles or 24 tiles or whatever. There's different color schemes there, even for the 15 puzzle. So there's ways to kind of look at it in terms of a permutation diagram. All of this stuff will also still work. So there's lots and lots of stuff to explore. And I hope that this will actually prove very useful for people who actually teach this stuff, right? So people who want to teach about permutations, who want to teach about parity, so they can use this app. At the end of the video, tell me what you think of this idea and how it worked out. So obviously today is quite different. I'm not going on a script. I kind of just say whatever I feel like saying. I mean, this is all sort of, the app itself is sort of scripted as it is, but what I say now is sort of off the cuff. All right. Now, I still want to do a proof of the swap property by swaps flip. And I also still want to do something about the Rubik's Cube. And let's just do the Rubik's Cube first. Again, the way I've presented it here in the app is very, very different from what you can see anywhere else. So what I've got here is I've got different views of this, actually 4 different views. The first view focuses on the corner pieces, and I've just labeled them. So 1, 2, 3, 4, 5, 6, 7, 8, right? So they all start out here, 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 here. And then I've got the 6 different ways of shuffling the cube using quarter turns, right? So there's, turn of the right side, quarter turn of the right side, or there's a quarter turn of the left side, or up, down, front, back, okay? Now all of those, let's have a look, in terms of permutations, right? So I mean, I've got those things kind of translated into a permutation diagram here on top, right? So if I kind of do right, I can actually check out, so what is this in terms of parity? It's odd. And in fact, all of those guys are odd, which is interesting, isn't it? So all of those guys are odd. And well, let's just permute this around and just talk a little bit about this. Right? So it's very neat, right? So it's cabled up, all of this stuff, so that we've got things turning and permuting and shuffling in unison here in the Rubik's Cube, but then also here in the permutation diagram. And actually in the permutation diagram, you now can extract some information. So for example, here what this says is that at the moment, the piece that starts out in position 1 should now be in position 4. Okay, so 1 is here, 4 is there. So this guy here is blue, yellow, red. So blue, yellow, red should now be here, so over here. So there's blue and red, and let's just turn it. And yeah, there's the yellow, okay? Or for example, the 6, yeah, the 6 should still be in 6th position, okay? 6 should still be in 6th position. Have a look. Oh, yellow here, orange there. That doesn't look promising. But actually, we're just talking about position, right? Not orientation of the pieces. So this piece here is what? Well, that piece at the moment is, well, at the bottom is the opposite of blue, which is green. Okay, so the green should be here, and that should be orange. So orange, green, yellow. Orange, green, yellow. So this should be orange, green, yellow. Well, there's this orange in here. Let's just take it. There's the green, okay? And if I go like this, there's the yellow. Okay, that's right. That's quite nice. But actually, more important for us here is that all these permutations are odd. Because then quarter turns, just like swaps, they behave just like swaps when it comes to parity, right? So when you kind of do, you know, one swap, then another swap, then another swap, parity flips, 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 flips. But of course, it's going to be exactly the same here for these quarter turns. Let's have a look here. Even, I do a quarter turn, odd, even, odd, even, odd, even, odd, even, odd, right? And so one of the things that's also going to be true is that if I'm, say dealing with an odd permutation of the Rubik's Cube in terms of locations of the divisions, it will take me an odd number of quarter turns to get it back to, you know, the initial position solved, sort of. Yeah. And well, let's just keep this in mind for the moment. Now, when I shuffle the Rubik's Cube and I kind of twist it up like this, of course, I'm not only permuting the corner pieces, I'm also permuting the edge pieces, right? And so there's 12 edges, so there's 12 edge pieces, corresponding permutation diagram. Let's just have a look at what happens here. So if I do a right quarter turn, that's also of odd parity. So even when it comes to permuting the edge pieces, quarter turns correspond to odd permutations. Not clear from the beginning, but you know, it is, right? So both in terms of corner piece permutations and edge piece permutations, quarter turns are odd. Okay, and so let's just see whether you got this also. If I kind of go like this, right? So there, 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 there. So at the moment we've got an even permutation. So what that means is it took us an even number of steps, an even number of quarter turns to get here. What can you tell me about the corresponding parity of the corners? All right. Is it odd or even? Well, obviously also even, right? Because we're doing a quarter turn that flips the both parities, okay? Another quarter turn flips both parities. So they both move from identity permutation to even to odd, even, odd, even, odd. So they're linked, right? So the parities of those two permutations, they're linked. They're always the same. So what that means, for example, about possible and impossible for a Rubik's Cube is this. So at the moment, it's completely solved, right? So if I take these two pieces here and swap them in the Rubik's Cube, I'm going to take them out and swap them over. And basically, we're really flipping the parity of the corners. And so the parities are no longer the same. And so what that means is that no matter what we do here, we can never get back to solved. Same here. If I take these two edge pieces and swap them, okay, swap them, then the parity of the edge permutation is odd. The corner permutation is still even, so we can't solve this sort of thing. So quite nice. All right, now something funny. So also not have anybody talk about it this way. We can actually do both at the same time, the corners and the edges at the same time. So I've labeled all the edges as before. They're basically 1 to 12. And then I've also labeled the corners 13 to 20. And now, okay, now as we permute things up, as we do quarter turns, things get permuted up. But see, the parity always stays even. And actually, when you think about this for a moment, that's probably not that surprising, right? Because, I mean, these corner pieces, they can't miraculously become edge pieces, and edge pieces can't become corner pieces. So really, what happens here is completely independent here on the left side, those first 12, and the right side, those last 8. And so if you kind of do this one here, you basically got separately here the edge permutation happening and the other one happening. And of course, since this is odd and this is odd and they don't have anything to do with each other, odd plus odd is even. So all of these guys here are going to be even, right? So a right quarter turn corresponds to an even parity permutation, and so on. Okay, and so now that's another way of looking at it. So you've got a Rubik's Cube, you kind of pull it apart, put the pieces back in, and then try to put them back into the positions where they started out from. And you know, if you happen to end up with an odd permutation after you put it together, you can be absolutely sure it can't be done. So that's very similar to the setup that we had with the 15 puzzle, where all permutations that we're dealing with are even. And then the one conclusion in this case was that, you know, when you kind of rip it apart and put it back together again, you've got a 1 in 2 chance of being able to put pieces back in order. And is that the same here, right? Is it the same here? You kind of pull it apart and put it back together again. Yes and no. Yes, in terms of location. So if you kind of pull this thing apart and say, well, just put the pieces back into their original locations, then if the permutation is odd, we can be absolutely sure not the thing. But to conclude from that to solve the thing, we need, anyway. So it's not the complete picture. And why is that? Because we still have to worry about orientations of those pieces, right? So this can go in like 3 different orientations here in the corner. This can go in 2 different orientations. And so actually when you kind of pull the Rubik's Cube apart and put it back randomly, you've got a 1 in 12 chance of being able to solve this. And for the moment, within that 12 is 2 times 2 times 3, we've actually only accounted for this 1, 2, the first 2. The first 2 in the 12 has to do with the parities, those 2 parities of the corners and the edge permutations. They have to be the same. So that says, okay, so some 2 there. The second 2 we can actually also get out of the parity, and that has to do with the fact that we can also label the stickers on the edges. So I've just done this here. Okay, if I label the stickers on the edges, then they will get permuted around. And it turns out that a permutation like this is also always even. Okay, so then what that means is, you know, if you kind of do a swap like this, which would correspond to an odd permutation of the stickers, that's also impossible. And so this outcome or upshot of the parity of permutations, that actually accounts for the second 2 in our 12. And then the last one can't really do this with parity of permutation immediately. And in a slightly different argument, I actually did that in the last video. Let's just go into this. Anyway, you get the idea, right? Main thing is, for permutation puzzles like this, you know, it's the wonder weapon. Parity of permutation is the wonder weapon to figure out what's possible and what's not possible. So only even permutations here, and there's a bit more involved stuff with the Rubik's Cube. Okay. All right. Now, before I do the proof, let me just quickly switch to the determinant business that I mentioned before. Okay, just quickly, okay, just to give you a bit of a insight into how you use the permutations and the parity to actually calculate the determinant, because most people, when they get talked about the determinant, they never get to this. So it's taught in a different way, and you'll never see the permutations, you'll never see the parity business. Well, as I said, you've got these square matrices, and you take all of the entries and distill them into this one number. And then the one number that has lots to say about different objects associated with this square array of numbers, the square matrix. Now, how exactly is this calculated? What's the function, right, that associates to these 9 numbers that one number here? Well, it goes like this. You write down all the permutations on the 3 numbers 1, 2, 3. So there's 6 of them, okay? Then half of them are even, half of them are odd. The green ones are the even ones. The red ones are the odd ones. And now underneath those permutations, you copy this matrix once, twice. So all these matrices are the same. And then you say, well, 1 is this one here, 2 is this one here, 3 is this one here, 2 is this one here, 1 is this one here, 3 is this one here. So you get the picture how these squares are highlighted, right? According to the permutations above the arrays. And now we just take the numbers in here and multiply them together. So 0 times 8 times 3 is 0, 8 times 6 times 3 is 144, 8 times minus 8 times minus 5 is 320, and so on. One more step. If it's an even permutation, you get a +1 here. If it's an odd permutation, you get a -1 here. Gives you 6 numbers, just add them up. That gives you the determinant. Pretty nifty, right? Pretty nifty. Okay, that was for 3 times 3. Of course, for 4 times 4, it gets a bit more complicated, right? There's a few more permutations here for 4 numbers, and then for 5, it gets pretty crazy here. There's like 120, but the scheme is exactly the same. And so for any n times n matrix, you can calculate the determinant like this, and it's magical. And why is it magical? Well, I'm going to talk about this in a separate video about determinants, which is hopefully not too far away. All right, enough with this. Let's just finish up with this business of swaps flip the parity. So how can we see this easily? All right, let me show you. So I've got a proof button here. Let's just press the proof button. So we've got 2 tiles. They're about to be swapped. And well, basically these 2 arrows in here, imagine that they're part of a permutation diagram, right? So part of a permutation diagram. And now let's just see what happens when I swap those 2 tiles. Okay? When I swap those 2 tiles, well, the arrows started out not crossing. They're now automatically crossing. So there's one extra inversion happening here, and definitely that would change the parity. Okay? But now this is not happening in isolations. Those 2 arrows, as we swap the tiles, they also interact with all kinds of other arrows here in the permutation diagram, and we have to actually have a close look at what happens there. Okay, so those 2 arrows, the tails, they separate the top into an interior part, and that's the exterior. And here at the bottom, the tips separate into an interior part and exterior part. And now there's a couple of cases for those extra arrows, depending on where their tails and tips end up in the interior, exterior. Okay, so that's the first case here. Exterior, exterior. So this kind of arrow doesn't have anything to do with those 2. And actually, when you swap, you can see it's not going to interact with anything. Right? So the only effect here on the parity is really that extra red crossing. Okay, next case. We could go from the outside at the top to the inside at the bottom. What happens when we swap? Well, we've got that green crossing here. We still got 1 green crossing. Nothing's changed, right? There's no effect on the parity. Next case. Yeah, so, it crosses twice. So outside to outside here, but in a different way. And so now we've got 2 crossings here, 2 green ones. When we cross, those 2 are still there. No effect on the parity. Okay, so I think it's the last case. Oh no, this one still. Okay, so 1 crossing here after the swap, still just 1 crossing, and this is definitely the last case. So inside to inside, and so far nothing is crossing, but you can actually see what's going to happen, right? How many green crosses will there be at the end? Well, obviously 2. But 2, when you add 2 to, that doesn't change the parity. So in the end, the only thing that has any effect on the parity is this. Going in, going out. Okay? And so at a glance, you can basically see why swaps flip the parity. And then this additional property that parities add like numbers, well, that's sort of an immediate consequence of this. And maybe I leave this as a bit of an exercise for you to fill out. So why is this the case? Just, it's pretty obvious, right? I mean, you've got first a permutation, you've got second permutation, right? And so the second permutation kind of now breaks down into, if it's an odd permutation, an odd number of swaps. So then to see what actually happens when we combine those two guys, you just go first permutation might be even, and then you kind of do an odd number of swaps, and where do we end up with, right? And then kind of just think about it a little bit, and it's going to be obvious that odd plus odd is even, even plus odd is, and so on. Anyway, maybe sort out the formal proof in the comments. So this is the end of it. Hope you enjoyed it, but let me know anyway whether this worked for you, whether it didn't work for you. And well, until next time, maybe with determinants, maybe with something else.